yeah, last time we just finished up talking about how you can kind of like, I mean, a function calls, and if the function returns a value, that function call will get replaced. Once it's done executing and that return gets hit, that function call gets replaced by the value it returns. Sometimes it returns nothing, which of course we learned means it returns this super special value called none. But sometimes it gives you a number, like for example, if I wanted to say sum of square, or square of sum, and then in the parentheses I say square of sum 2, 2, and square of sum 3, 3. Well, square of sum 2, 2 is 16. And square of sum 3, 3 is 36. So that would just be replacing this with the 16 and this with the 36, and then I can call square of sum again, and it gives me 2074, 2,704, pardon me. That's all. And I need to say again, if you're looking to connect some dots here on like, oh, all this complicated, no, you're working too hard. Don't connect dots that don't exist. All it is that function calls, you returns a value. You give a function input, the arguments you provide to it, it does its number crunching, and then it returns the value. Functions, you put information in, you get information out once it's done. That's the idea. And that's all that's happening here. Obviously, we can't compute what sum of square all of this is until we know what sum of square 2, 2 and sum of square 3, 3 are. But Python will go do all that in the correct order to get it working. Okay. Variable scope. I know I already talked about this. If you define a variable inside a function, it only exists inside that function. So if we look at the code here, the parameter, temp in Celsius, partial conversion in temp in Fahrenheit, those three variables only exist in that function. If outside the function, I were to try to access the variable partial conversion or temp in Fahrenheit, I can't. If I call Celsius to Fahrenheit with the value 28, it goes and calls this function. And inside that function, we see there is a variable called temp in Fahrenheit. And it's going to have the value, whatever this gets resulted in. But I can't access that variable directly. I can't. It only exists inside that function. If I tried, Python would say name error, temp in Fahrenheit is not defined. Because Python's saying, I'm not aware of a variable called temp in Fahrenheit. And you're going to say, yeah, but it's right there. It's like, no, but Python can only look in the scope it's allowed to at that given time. If Python is writing the code inside the function, it's entirely aware of all the variables inside that function. If Python is running code outside that function, like in this example here, we did the function call, and immediately after, we try to access temp in Fahrenheit, it's going to say it doesn't exist. Where this can get hairy is if you end up having variables with the same name in two different scopes. There's no rules breaking. What I just said still stands. But if I were to run this code, see, point I'm making here, see how on line 1, 2, 3, I say temp in Fahrenheit equals whatever that is? There's a variable inside that function, Celsius to Fahrenheit, called temp in Fahrenheit. But you'll also notice on line 6, I've got temp in Fahrenheit also equal to the string hello world. So on line 7, I call the function, and then of course in that function, you've got the variable temp in Fahrenheit. It has a value, that function finishes, the variable's gone. When I hit print temp in Fahrenheit, it's going to print out hello world, because it's entirely unaware of the variable that was defined inside, the variable and the value it had that's in Celsius to Fahrenheit. It's only going to work with the variables it's aware of. You can't have two variables with the same name in the same scope. You can have two variables with the same name as long as they're in different scopes, but that could cause some issue. Because if you're expecting it to say whatever the temperature in Fahrenheit is, you've got a problem. It's going to say hello world in this case. There is a way to set global parameters, meaning you can set it somewhere and then the code everywhere knows about it. There is a way to do that, but don't. That's a recipe for disaster. It's bad form. Just because you can doesn't mean you should. Don't do that. We won't be doing it in this course. Now, import. All of you have done this so far if you've been to one of the labs. Python, you know, when you load up Python, it provides a bunch of functions to you by default, right? There's print, there's input, there's a bunch more. There's abs for absolute value if you care. It's got a whole bunch of functions that as soon as you turn on Python, it provides to you for free. You didn't have to write those functions. And the reason it gives it to you for free is they're remarkably popular functions that your average programmer might want. But there's also a hell of a lot more functions that Python has available to you for free. A lot. But the trouble isn't maybe the right word, but chances are those get used in more special cases. They're very popular, a lot of people use them, but your average program doesn't need to know square root, for example. But your average program probably wants print because it's so common. So you load up Python, you get print, but you don't get square root for free. But don't worry, all you have to do, because Python does have a square root function for you to use, but in order to use it, you have to tell Python explicitly, okay, I really do want to use a square root function, so I'm going to load in the module called math. And the math module contains a lot of math-related operations and functions you might want to use. In fact, you can go click here, I got a link to it, it'll take you to Python's math module documentation. And you can look, if you wanted, you can look at all of the functions it provides to you. All you have to do is import math, and then you can call math is finite, math square root, math mod f, math perm, math prod, math remainder, math trunk, math ulup, I don't know what that is. Return the value of the least significant bit of the float x. Let's not worry about that. There is a lot in here. And all of these functions, they're great. Look, there are a lot. And it's not great. Oh, and there's also constants, like pi, for example, where I know I saw a lot of people when you were doing some of those things like area of a circle. You just hard code it saying like, well, pi is 3.14. That's fine. But if you wanted to get super geeky about it, you can import math.pi. You can import math, so you can use math.pi, which just gives you the value 3.141592, ... So it'll be a much more precise one, but for your purposes with calculating area of a circle, 3.14 was fine. The reason Python puts these in modules is one, this module is kind of like this coherent set of things. It's all the math-y stuff, right? There's a bunch of other modules out there. There's a strings module for fancy extra stuff you can do with strings that your average program won't use, but maybe you do. And if you do, you import strings. I can't remember if it has an S on the end. The point is, Python, when you load it up, it imports all those functions for you by default, do things like your print. But it doesn't want to import more than it needs, right? Otherwise, your program gets bloated. It gets really big. There's extra stuff there that you don't need, so it doesn't include it. But if you really want it, you just import it, and then you have full access to it. If you wanted to really see what you have in there, is you can look at the Python standard library, which I linked to here, but you could just go Google it. And you can get a sense of all the different things in here. So, look, there's a math module, there's CMath module, there's decimal, fractions, random, statistics, numbers. There's all these, there are a lot of modules. There's the string one. There are a lot you could import if you really want it. It's great. And it's kind of good to have a general high level of some of what's available in here, because let's say it's a couple years from now and you're writing a program and you think, you know what, I need a function to do X, Y, Z. And you start writing a function to do X, Y, Z, and it's a tough function to write. You know, it takes a lot of work. And then your colleague comes up and says, why'd you write that? Python gives it to you for free. All you have to do is import math. You're going to say, oh, man, why did I do all that work? So it's kind of good to have a sense of what functions already are provided to you. And it's easy to find because Google exists. So import. That's what we do. So we can import math. to get the square root, for example, math dot square root. If I go here, let's just go down here. If I say import math, I'm just going to go new cell so I know it's run. Math dot, and if I do dot, collab will populate this drop-down list of all the things I can do. See what happens if I do dot pi. Right? I wonder what's going to get printed out. There you go. I guess that's how precise it gets. 3.141592653589793. Great. It's there. Cool. There's a lot there. It's great. Has anyone did anyone, when importing math, do it this way? Oop. Nope. Something like that. You did. Only one? All right. Doing it this way is entirely fine, but there is potential. So, did you do it like this, or did you do this? Like that. Okay. This would be a better way to do it, arguably, than the star one. When you say from math import star, it means import everything. If you really only want the math function, you can do it this way, where you say only from there only import this thing. But it works a little bit differently. This would be more similar to saying, just like pretend that you've literally copied the code from the math module into your code, so it's there. And if you wanted to call square root, before I hit run on this, if I wanted to do square root, nope, math.sqrt, 2, hit run. Great. If I do it this way, you wouldn't need to include the math dot in front of it. You could say math, print sqrt over 2. So in this particular example, I don't need to preface it with math dot. But I'm going to recommend against doing it this way for now. I'm going to recommend you do it import math, and then anything you want from the math module, you say math dot. The reason I recommend that way, and it's the only way I discuss here, is because, again, there's nothing wrong with doing it that way. It's entirely fine, and there are cases where it is definitely better to do it that way. But for our purposes, it is entirely possible. It's happened to me, it's happened to a bunch of programmers, that let me show you. There is another package out there. There's another module called Numpy. Okay? There's math, and then there's Numpy. Numpy's another one that does a lot of math stuff, but it's designed for certain things in a certain way. Okay? And if I look up Numpy square root, there is a Numpy square root. So if I do it like this, and I wrote print we see that answer. And if I ask you the question, where did that square root function come from? The one that you ran, where did it come from? You say, well, it's the Numpy one because you said Numpy in front of sqrt. I could change it very easily to say math.square root. And now, it gives you the same answer. Now I would say, okay, if I ask you, well, which square root did you run? The one from Numpy or the one from math? You go, well, the math one, because you said math dot, and I know that means it came from the math one. But if I did, come on, from math and I said print, and I ask you, well, which one did it run? The one from math or the one from Numpy? What's your answer? Do you know? There is, you don't know. It's ambiguous. It could come from either. The previous example, you have to be very explicit about where it came from. With this, you don't. But that can lead to ambiguity. And the last thing you want in a program is ambiguity. Where if I ask you, did I run the Numpy square root or the math square root? I don't know. I can't tell you. They gave you the same answer, great, but what if it matters to me? I need to know which one it's running. I don't know. So this is where that from math import can become sticky. So to play it safe, just use import math and then math dot. Again, there's nothing wrong with doing it that way. It's just, it could lead to issues. All right. The last thing I think in the topic that we have here is comments. Nope. Don't need that. Comments. You've already seen this. I know I've shown you code with comments in it. A comment is a way to add text to your program that Python entirely ignores. Python won't run the line of code that has a comment on it, or that is a comment. You see that number sign? Calculate the Euclidean distance between 2 points. Great. The reason that comment exists is you come along and you start looking at that. D equals x1, what is that? What is that? You read that comment, you know exactly what it is because it's described in English there. So comments are a great way where if you have some code that might be a little unclear, that's not obvious from the get-go about what it's doing, throw in a little comment there to say, oh, this is calculating Euclidean distance between 2 points. So another programmer can come along, or you, 1 week from now, comes along, you look at your code and go, oh, yeah, okay, I know what that does. Great. So a comment is a nice, handy way to add descriptions of your code to your code. Python doesn't run that line, it skips it entirely. But the point of that line of code, that's the comment, is for a human, not for Python. If, however, so when people start learning about comments, you have to comment your code. You have to. You will lose marks if you don't comment your code. But it always then turns to the question, well, how do I know what to comment? To play it safe, you could say when in doubt, comment it. But that always leads students to writing me like a comment for every line of code, which is entirely unnecessary. You only really need comments for lines of code that are not clear. A line of code that your average person wouldn't figure out based on what the code is. Because first, we want the code to be very self-descriptive. We want our variable names to be very clear, such that you can look at that line of code, just code, and know what it is. In this example, instead of calling it d equals, maybe I should have called it Euclidean distance. And then any person looking at that line of code would say Euclidean distance equals that. Oh, that's just the way to calculate the distance between 2 points. I probably wouldn't comment that line of code if I had a better variable name. But you will run into cases where lines of code start to get a little complex. So we have comments just to eliminate any issue with understanding what it is. So these are one-line comments. You can have multi-line comments. And a classic example of this would be something we call a docstring. These are super, super, super special comments that actually have a very important technical purpose that I'll talk about in a moment. But what we'll do is we write docstrings at the beginning of every function we ever write, unless it is insanely obvious what it's doing that you don't need it. Chances are your functions aren't insanely obvious that you don't need it. You're going to want a docstring no matter how simple you think it is. The purpose of the docstring is to explain what the function does. As you write code, you see you're going to be using a lot of functions. Not only functions that are provided to you, but functions that you've written as well. And we want anyone, including yourself, a week from now, to know what each function does very clearly. What the function does, what its parameters are, like what input does the function want, and what output do I expect from the function. That's what we talk about in docstring. So if you look at this example, Celsius to Fahrenheit, convert a temperature from Celsius units to Fahrenheit units. Okay, great, that's describing what it does. And then you'll see param temp in Celsius. That is a description of what the parameter is temp in Celsius. And it is the temperature in Celsius to be converted. And what does it return? The temperature in Fahrenheit. That's what we have. That's the docstring. And that is the convention you follow. Mind the use of the colons. Mind the use of the 3 quotations. Those are all required there to do it the right way. And here is the technical advantage of using docstrings. By the way, you have to use docstrings. If you don't, your program will run, but if you don't, you'll lose marks. Let me show you an example. If I go down here and I write print, and I wait a moment, you will see Colab gives me this pop-up here. This pop-up is the docstring that someone wrote for that function. When we were looking at that math module, the Python documentation for math, and there was a description of each function, that website is automatically generated from the docstrings in the code. No one wrote that website. Someone said generate the website, and it got generated automatically based on the docstrings. What's cool here too is you'll see like, okay, print whatever, prints the value to a string, or to system standard out by default, optional keyword arguments, and includes all this extra stuff that doesn't matter to us. Watch what happens if I say, oh wait, I don't have a docstring. So if I say, nope, and I just hover, it doesn't give me a lot of valuable information here. If alternatively, I'm going to just take this as the example. So we've got that function, and now Celsius to Fahrenheit. If I wait, look, converted temperature from Celsius units to Fahrenheit units. Parameter, temp in Celsius, the temperature. So it's telling me what it is. That docstring is used to generate this little pop-up. Because whenever you're using a function, you might say, what is the order of the parameters? What does this parameter mean? What does it do? What do I expect as the output exactly? It pops up here for you. Docstrings are fantastic. You gotta write them. You are gonna say, okay, you just told me when you're writing comments, you don't need to write comments for things that are painfully obvious. And that function is painfully obvious because it's called convert Celsius to Fahrenheit, and it takes temp in Celsius. I know what it's gonna do, fine. But with functions, because functions are these like nice units, it's always good to have a description of that nice unit, no matter how simple you think it is. Questions about docstrings? Yeah, great. Write your comments. If you don't, it's a joke in computer science about, oh, I forgot to write comments. I don't understand. Like, the jokes are this. I included 2. They're not particularly good ones, but like this is what you will find on the subreddits like programming humor. Like, oh, I don't remember what this code does. No, you won't. You're going to blow it. You're going to forget. It's a joke about how you always forget no matter what you say to yourself. Any questions about that? Okay, the next topic is propositional logic. If you're following along and you hit next and it's called like testing, just go back to the main page and make sure you do propositional logic. I changed the order of the topics this morning, and if your web page cached, it might be out of sync. Just refresh your page, it should fix. Propositional logic. I'm going to talk really technical about something you are already all familiar with. I know you are. There are some statements that are true and some that are false. For example, this course focuses on introductory computer science. That is a true statement. The topic of this, the title of this topic is not logic. Well, that's false because it's propositional logic. Like, it's not logic. It's a rather intuitive thing, since these are things you're already familiar with. And these ideas, like there are statements like, am I wearing shoes? True. Like statements are true and false. True and false are a value to computers. They have their own type. We saw integers, we saw none type, we saw float, we saw strings. Now we know a new type, and this is called a Boolean. It's named after someone. A Boolean. Booleans, unlike integers, which can have like a bunch of different values, and none type, which can only ever take one value, a Boolean can only ever take one of two values, true or false. There's nothing in between, and there's nothing outside. It's just true or false. And we have operators for Booleans. Just like how we have operators for numbers, like 1 plus 1 plus is the operator for addition. We have three really good ones that we use very commonly for Booleans: and, or, and not. This is going to, again, this is going to be overly detailed of something you're already going to be remarkably familiar with. This is what we call a truth table. The way we read the truth table is, see on the far, like the A and the B columns. Not the A and B column, but we've got the first column there that says A, and then the second column that says B, right? A and B are our statements that might be true or false. Like, am I wearing shoes? Am I wearing a hat? That's what those are. If we ever have the case of something that's true, and B is true, and then if I say, hey, is A and B true? You say, yeah, it's true. If I ask you, is A or B true? You're like, well, yeah, they're both true, so it's true. And then if I ask you, well, what's not A? If A is true, what's not true? Say it. False. That shouldn't have been difficult. Now, if let's say you have A being true, but B is false. A and B, that's false. A and B, and will only give you true if both things are true. But or will give you true unless both things are false. And not is probably the obvious one. You just flip what it is. If it's true, it becomes false. If it's false, it becomes true. This is overly technical. This is a very abstract description of something I'm going to quiz you on right now. Is the sky blue and is water wet? Answer me. Yellow? No, never say yes. You got to say true. It's true because, well, is the sky blue? True. Let's assume it is. Today it's kind of dark and I don't know. Is water wet? No. Yes, it is. No, it's not. You're not allowed to say not anyways. It's either true or false. So you're wrong either way. It's false. It's false. Well, you're wrong. That is a false statement. Is water wet? Of course it is. Except you disagree. So if we have a statement that's true and a statement that's true, we use and, we get true. You probably never ever thought about this basic logic in breaking down each statement to like, is the sky blue? True. Okay. Is water wet? True. True and true. Oh, that's true. You don't think like that because you operate more abstractly at, is the sky blue and is water? Yeah, it is. Like you don't need to break it down like that, but the computer does. So if I have a statement, it's got to get boiled down to true or false. Then if I have trues and falses, I can use these Boolean operators like and or and not. Is the sky blue? And is it over 100 degrees Celsius outside? Who just said no? Corrected yourself. Good. Well, that's a false thing entirely because although the sky is blue, it's not 100 degrees Celsius outside. Therefore, the whole thing is false. Is the sky blue or is it over 100 degrees Celsius outside? True. Sure, it's not over 100 degrees Celsius, but the sky is blue, so it's true. Only one needed to be true for or. Now, one thing that trips people up is sometimes people, when they first learn this, they kind of get confusion on exclusivity. On, well, if both things are true, is or still true, or is it false? For our regular, ordinary or, it'll be true. If both things are true, am I wearing shoes or a shirt? Yeah, it's both. It might sound kind of funny. If you really want the case where it's like, well, if they're both true, it would be false. We would use something called exclusive OR that we're not going to talk about right now. And it's not very common. Regular OR is just false. It's always true unless both things are false. So if I do a test, am I wearing a watch or a hat? I'm not wearing a watch. Answer me, come on. It's too early in the semester to be this tired. False, thank you. Is it not over 100 degrees Celsius outside? True, because the statement, it's 100 degrees Celsius outside, is false. And what's not false? True. Is the sky blue and is it not over 100 degrees Celsius outside? True. Well, because it's not over, okay. Being over 100 degrees Celsius outside is a false statement, but we knotted it so it's true, and then we have a true statement and a true statement. In fact, this is an example of suddenly like composing Boolean operations. We use an and a not in the same sentence. You may have observed that for and, both statements must be true. For or, one statement must be true. And not just changes true to false and false. Yeah. For or, both statements being true produces true. There's another operation called exclusive or that is true only when one statement is true. We're not going to worry about that. I'm just noting it here in case you're interested. Boolean types. They have their own type. If I were to type in true, and hit run, we see this true pop-up. But notice it's not a string. I didn't put it in quotes. Do not put it in quotes. Because if I put it true in quotes, it's just the string true. It has an entirely different meaning. Just true is true. Same thing with false. False is just false. And if I ask, what is the type of false? It'll say bool, for Boolean. So it's a new type, a Boolean. And it can only ever have two values, true or false. If you ever see something like this, and it says, what, true is not defined. Yes, it is. He just talked about it being like a type in Python. It's got to be uppercase. This is kind of annoying because in some programming languages, it's got to be lowercase, and in some, it's got to be uppercase. Deal with it. In Python, it's uppercase. Long story short, you ever see something like this, and you're like, but it's true, it's a Boolean. Chances are, it's just, it needs to be uppercase. In fact, if I hover, I'm curious if it's going to be like, are you sure you don't mean? All right, it doesn't say anything. That's okay. Okay, Boolean operators. Just like math, like our arithmetic operators, plus, minus, divide, multiplication, we have Boolean operators. So with an arithmetic operator, like addition, it takes two numbers. It takes a number, another number, it adds them together and gives you a number. It takes two numbers and it gives you a number. You can think of operators as just like functions, except we just kind of, the syntactically, they're a little different. Because we don't write add, open bracket, the two numbers. We just say A plus B. But addition takes two numbers and it produces another number. We saw the operator with the plus sign on strings. So obviously we would say, like, okay, the plus works a little differently depending on the types. In that particular case, we say it's context sensitive. If it's addition with two numbers, it's addition. If it's the addition with two strings, well, it's concatenation. It works differently depending on the types. But, and or, for example, are Boolean operators. Instead of taking numbers like arithmetic operators, it's an operator that takes two Booleans and produces another Boolean. Right? Boolean and Boolean will give you another Boolean. There are other Boolean operators, though. Comparative operators. Where we can take two numbers, or just two values, and get a Boolean out of it. So I can ask a question. For example, I could ask 5 greater than 3. I'm using the greater than symbol as an operator. But this operator takes two numbers and gives me a Boolean, which is a little different because with arithmetic, you take two numbers, you get another number. With the and or, you take two Boolean and get another Boolean. But with these comparison ones, it's funny. You take two numbers and it gets a Boolean, which is interesting. So, is 5 greater than 3? True. We could type that in. 5 greater than 3. True. Is 5 less than 3? Yell out the answer. Everyone yell out the answer. False. Look, you were right. Python confirmed what we suspected. 5 is in fact not less than 3. Now, if you're looking at this and you're saying, well, I mean, that's kind of a silly statement to write. Is 5 less than 3? Because like, you've hard coded the value is 5 less than 3. Is 5 ever not going to be less than 3? No, that's not how our universe works. But of course, we can do this with variables. I can say a equals the int of input, and then print is a greater than 5. Let's run it. Oops, I got an extra space there. And if I put in a 2, it'll give me false, because, well, 2 is not greater than 5. If I run it again and give it 55, it says true. Now here's a real test. And this is a really good test I'm going to give you for trying not to connect dots. Simply, what does the code say? And it kind of is a trick question, though, I will admit. I'm going to hit run, and I'm going to enter the number 5. When I hit enter, what will happen? Raise your hand if you think it'll say true. No one? Raise your hand if you think it'll say false. Well, how is that? Well, it does say false. Why? Well, answer the question. Is 5 greater than 5? No, it's not. It's equal to it, but it's not greater than. So greater than and less than are two operators that can take the numbers and give you a Boolean. You can do greater than or equal to. Now, if I say 5, will it say true or false? True, because 5 is greater than or equal to 5. That's greater than or equal to. You can do less than or equal to. Is 5 less than or equal to 5? True, it's equal to it. But of course, if I put in a 66, well, it's false because 66 is not less than or equal to 5. You can ask not equal to. It's an exclamation point with an equals. That's a way to ask if two values are not equal. So if I put in 5, will this say true or false? Uh-oh. Just all you have to do is ask the question, is 5 not equal to 5? False, because 5 is equal to 5. That's a silly question. Is 6 not equal to 5? Why? Well, 6 isn't equal to 5, so it's not equal to 5. And lastly, equals is the way we check for equality. Are these two values equal? This is the equals that the mathematicians might be more comfortable with. This is the equals that is actually caring about equality. Are these two values actually equivalent? So, if I'm going to get rid of the input thing. I'm just going to hard code some values now. Does 5 equal 5? True. Does 7 equal 5? False. It's checking if these two values are in fact equal. The statement of equality will be true or false. It's another Boolean operator. It takes two numbers and it gives you back a Boolean. It's a comparison operator. Single equals is assignment. 2 equals is a check for equality. So if I write 7 equals 5, it's just not going to work. It's going to say keyword can't be an expression. Like, I just can't. What? That is nonsense code to Python. What you meant here was equals equals probably. Python is, as a quick little anecdote, Python's pretty nice. So like, imagine I had a variable a, right? If I had a variable a, and I wanted to check if a is equal to 5, this code doesn't work. Python's going to say, yeah, it doesn't work. Because I didn't check for equality. I used equals as if it was an assignment, but you can't use an assignment like that. Some other programming languages, some older programming languages, this code will run just fine. But it could cause some really big issues in your programs. But we will be able to talk about next topic. But what other programming languages would do is assign that value. And in those languages, what will happen is if you ever do an assignment, that assignment actually just continues to return that value. So if you say a equals 5, when Python runs it, it puts the value 5 into a, and then it also returns 5, but if you don't do anything with the 5, it just kind of goes into oblivion. And in other programming languages, the older ones, there's no such thing as true or false. There's no Boolean type. The convention would be you just use an integer, okay? Or you could use a single bit. But you typically use an integer where 0 means false, and anything that's not 0 is true. So it might think that it might actually return the wrong value. We could talk about this later. This isn't going to affect you at all. We're using Python. It's happy. We're happy. Okay. Yep. So we've got equals, not equals, greater than, less, greater than equal to, less than equal to, and so on, so on. We'll skip that activity. And this is just the warning. Equals equals is for equality. Single equals is for assignment. And there's nothing stopping us, just like with our basic arithmetic, how you could say a plus 17 divided by 14 to the power of 44, all multiplied by the value of b, and you can compose all those operators into one big long expression. You can do it with Booleans as well, with Boolean comparison operators and Boolean operators. Right? So if I have 17 plus 2 is less than 18, or 17 not equal to 18, you're going to look at this and be like, whoa. The same thing applies to your basic math. Just chip away at each individual little piece. We can break that down. Well, 17 plus 2 is 19. Is 19 less than 18? No, we could say that's false. And then we've got the 17 not equal to 18. Well, that's true. So we have false or true. And what's false or true? True. There. Here's another one. Does 101 equal 100 and 66 minus 17 less than 54? Well, let's break it down. Well, 101 does not equal 100, so that's false. And then we have 66 minus 17. Well, we can turn that to the 49. And is 49 less than 54? Well, that's true. So what's false and true? False. So you take your time and just break it down. We could do this forever. Is 14 greater than 0, or is 6 not equal to 7, and is 4 plus 17 less than 20? All right, well, 14 is greater than 0, that's true. Is 6 not equal to 7? That's true. Okay, 4 plus 17, that's 21, so it's 21 less than 21. Okay, so that's false. And then we have true and false. What's true and false? False, so that becomes false. So we have true or false. That whole thing is true. My goodness. Now, I will say something. If you ever write code that looks like this, there's nothing wrong with this code, but chances are, if you're, like, these are examples that are designed to be overly cumbersome as being just an example, showing you that you just follow the steps. Chances are, though, when you're writing your code, you're not going to have Boolean expressions that beefy. If you do, you might be doing something wrong. You might want to break it down into steps as you go. This will become a little easier to kind of wrap your head around once we see more examples in useful code. But chances are, if you're looking at that going like, man, I don't want to simplify that, yeah, no one does. And chances are your code wouldn't have anything that weird and ugly in it. It would be a little cleaner. Yeah, there's the note. All right, cool. And then the next thing we'll talk about tomorrow, it's a smaller topic, is the testing stuff. So, see you all tomorrow.